Welcome back to VLSI technology lecture. So in the last lecture, we have already discussed about the molecular beam epitaxy. We have seen the details how different materials can be, means the epitaxial layer of different materials can be grown using the molecular beam epitaxy. In the today's lecture, we have to discuss about the one of the very popular structure, which is called as the silicon on insulator (SOI) structure. So we have to look at why this structure is so popular, how this structure is actually fabricated, what is the need of this particular structure, okay, and what are the advantages that this structure is offered as compared to some other structure. So that we have to look at. So to start the silicon on insulator structure, first of all, we have to discuss about the inverter structure. Okay, so basically, as we already seen, the NMOS fabrication technique using the metal gate process in previous lectures. So we have to see if we are following a particular processing fabrication steps for making a particular circuits, then how our CMOS devices will look like. Okay, inverter is actually composed of PMOS and NMOS. So CMOS is one of the basic element, as we have already seen for ICs. So most of the circuits can be composed of interconnecting the different CMOS devices. So just to start with the SOI, we have to first discuss about the basic CMOS structure. So let's begin this particular topic. So here I have taken this picture, okay, for our inverter. Okay, so our inverter is basically composed of PMOS transistor and NMOS transistor. They are connected in series, and then we have to apply a certain voltage at one of the input port, and then from the other port we have to take the output. Okay, so this is actually while fabricating this type of device, as we know that we need to have both type of transistors. Like we also need PMOS transistor as well as NMOS transistor within the same substrate. So how this particular transistors are actually fabricated. So whatever steps that I have discussed for NMOS fabrication, the same steps are to be followed for fabrication of the CMOS also. Okay, so in this structure, what we can see is, but only one basic difference that we have to keep in mind is while making the NMOS transistor, we, if you recall, we had taken the substrate should be of P type. Okay, as you can see, while making the NMOS transistor, our substrate should be of P type, and within this P type substrate, we have to dope a certain islands of n-doped dopants we have to make. Certain regions we have to make that should contain the n-type dopants. Two such regions we have to take, and in between there will be a p-type substrate. So that will be acts as a channel that should be inverted while the operations. Okay, and one of the terminal will become your source, and another will be becoming a drain terminal. And similarly, we can make the various contacts. Okay, here the gate we have taken as the polysilicon gate. Okay, we have taken the polysilicon gate. So as we know, if we have to fabricate the NMOS transistor, we have to take the P substrate. In a similar fashion, if we want to make a PMOS transistor, obviously what we need is we need to have a substrate of N type. Okay, so onto the same wafer, because either we can go for the N type wafer or we can go for the P type wafer. Okay, P type substrate. Okay, so if suppose we have started with the p-type substrate, then obviously we can directly fabricate the NMOS transistor. But for fabrication of the PMOS transistor, we need to have particular well structure. Okay, here we have taken the N-well structure. So first of all, we need to grow this N-well. Okay, so this is generally called as the well technique. Okay, well technique of making the CMOS transistor. There are so many techniques, okay, in which one of the technique is N-well technique. So in this N well or P well, if we are taking the N type substrate, then we have to go for the P well technique. So here we are using the N well technique. So before starting the fabrication steps, we have to first grow this N well layer. Okay, that can be done by diffusion process as usual that we do for this type of drain or source. The same type of diffusion steps must be there to particularly grow this N well. The only difference you can assume is that here the depth of the drain and the source is less as compared to this N well, because within this N well we have to make the complete transistor. So this is when well first we must be grown first, and then within this N well we have to grow the EMOS transistor. Okay, and here we have to form the NMOS transistor, and then we have to make all the connections, necessary connections. So basically this particular circuit is our CMOS transistor, and basically it is denoting you the inverter. Okay, this is basically your inverter. So once we have this type of a structure, uh, we have to again follow the same fabrication steps that we have followed for the NMOS transistor. So please do not confuse with it. Okay, the same processing steps. There may be a multiple times we have to use the masking and photolithography operation. Multiple times we have to perform the etching. Okay, and then finally we have to arrive at this particular structure. So now what you can see here is basically when we get this type of a structure by using the unwell technique, there is certain disadvantages that we have to look at. So what are those disadvantages that we have to concentrate upon? Okay, so you can see within the same substrate we have grown the anvil and then we have fabricated the devices. Now because you can see here we have one of the transistor, and in this region we have another transistor. So here you can see we have this metallic connection. Okay, from this metallic connection we can take out one lead and then we can make a certain connections, right? And then we can make one connection from here, another connection from here. Okay, so what we can see is then if you recall the inverter structure, then this gate is tied together, then we have to apply the input, we have to take the output from this terminal. Okay, so that way we can take out the output. So what you can see in this particular structure is wherever we are having a MOS transistor, whether it is NMOS or PMOS transistor, there you can find that there is a very thin oxide is existing. Okay, like in this case in the NMOS transistor you can see here we have the transistor area, and here this is our thin ox. Okay, in between the gate terminal and between this p-type substrate, which is going to be converted into a channel. Okay, so we have to invert it, make it conductive. Fine, so here we are having a very thin oxide. Okay, again here you can find out there is a thin oxide. Okay, but what about this area? Okay, just to assume it. Okay, what about this area? So this area is left out. Okay, and here you can see that again in this area we do not have any transistor that we want to fabricate deliberately. We do not want to fabricate any transistor over here. Fine, but you can see this area is actually covered with a thick oxide layer. It is again a oxide layer as the layer we have here, but this oxide layer is very thin, but here we have a very thick oxide layer. Okay, so basically those area or those uh, channel you can say, or those substrate regions where we do not want to have a particular transistors, then those areas should be covered with a very thick oxide layer. Okay, so normally thick oxide layer, what it do is it actually make the threshold voltage very high. Okay, therefore this area means rarely get converted into channels. Okay, otherwise there may be some detrimental effect may take place. Okay, so instead means even after that what we can see is there is a deliberately made one device here and another deliberately made devices, another is here. Okay, so here we have the body connection for this particular transistor, P plus region. Okay, substrate tapping we are having, another well tapping is at this point. So that is our body connections. Okay, but now we can see into in another picture that basically even after making this type of structure, these two MOSFETs are not electrically isolated. Okay, they are not isolated. Okay, and there may be a chances that there will be a certain parasitic component that may exist because of this structure itself. Okay, why? Because these two transistors are not isolated perfectly. It is not electrically isolated. Okay, so because of that there may be a certain parasitic component. It may be like you can see that here it is a junction, n plus and p junction. Another p and n junction could be formed at this point. Okay, another you can see again it is forming a certain type of junctions. Okay, p plus and p n layer. So again it is forming a junction. Okay, so altogether, there may be a certain instances in which this entire circuit may be making a certain combination of the components, and that component is going to affect the device operation. Okay. For example, we can see basically what happens is we can take this n plus, this p plus region, and this n well. Okay, so taking this all together, okay, it may form an npn transistor. Okay, it may form an npn transistor by taking this our drain diffusion lands. Okay, this is our diffused lands. Okay, so diffused and our drain, and then our diffused p type region. Okay, and this is our substrate region. Okay, and then this is our n well region. Okay, so this n plus and this substrate and this n well can be acting like an npn transistor. Okay, and this particular area will give you this particular region may offer you a certain resistances between the p plus and p. Okay, this may give you a certain resistance path. Similarly, here you can again see this is n type well. Okay, this is our p type material. Okay, and this is again your p type substrate. So again this is forming another transistor which is your PNP transistor. Okay, so this type of structure may be possible. There may be a certain parasitic elements or parasitic circuits that may exist within this particular uh, device. Okay, because these two transistors are not isolated electrically, and because of this there may be a chances that a circuit may form a low resistance path. Okay, and because of the means existence of this type of parasitic element, whatever the functionality that we want from this device, that is going to be affected. Okay, that is going to be affected, and that is going to affect, and because of this whatever the function that we want to get from this device, obviously in a certain electrical condition, when we apply a certain voltages, okay, at VDD we are applying a certain input voltages at the gate terminals. Obviously if this resistive path gets turned on, okay, low resistance path gets turned on, then obviously it is going to have another conductive path, and because of that it is going to affect the performance of the devices. Okay, so basically this particular problem is called as the latch up problem in CMOS. Okay, so since the latch up problem is not there in our syllabus, so I'm not discussing it in very detail, but just you have to understand this fact is because of this type of a structure, and because the PMOS transistors and the NMOS transistor made in this fashion are not electrically isolated, there may be a certain parasitic components that may exist within the device. And because of these parasitic components, because these components we are not fabricating this transistor, we are not fabricating this transistor, but because of this structure itself, okay, these transistors are comes into the picture, and now it is forming a particular low resistance path, and then it is going to affect the device operation. So this is not the only thing that a parasitic transistor is there. There may be a certain parasitic capacitances. Okay, that may be available within the device. Okay, and that is going to affect the speed of the device or the performance of the device. Fine. So the objective of this, so basically here you can see we are writing it as a bulk CMOS structure. Okay, so generally in the CMOS structure we are taking a conductive substrate. Okay, and why this is making a low resistive conductive path, because it is a conductive in nature. The p substrate that we have taken over here, it is a conductive substrate. Okay, and generally when we have this type of structure, conductive substrate we have, that time it is called as the bulk CMOS structure. Okay, so basically this problem is existing because these two transistors are fabricated on a particular conductive substrate, and these two transistors are actually not electrically isolated, and that is going to affect the device operation because of the parasitic components. Okay, now our main purpose in the silicon on insulator device is actually the isolating the two transistors. Okay, we have to isolate them. Okay, in such a way that these two transistors should not be interacting each other. Okay, so that it should not go to it should not able to affect the device operation. Okay, so basically we can have another structure of the same transistor, CMOS transistor. Okay, this is our SOI inverter cross section I am showing. Okay. So a silicon on insulator inverter cross section. So till now we have not discussed what is silicon on insulator, but just try to understand here is that what is the difference between this and this. Okay, that you try to understand. The top structure you may it look like very much similar to what I have shown over here, but the thing is, what is the basic difference is, here we have taken a p-type substrate. Okay, and then this particular layer is our insulator. Just see this one. This particular layer is our insulating layer. Okay, this is our insulator. Okay, right now I am not discussing what kind of insulator it is. It may be SiO2, it may be silicon nitride, Si3 and 4. Okay, it may be a different type of insulator that we may have. Fine. So basically this particular layer is uh, our insulator. Fine, and this insulator, within this insulator we have to grow a very thin layer of our silicon, and within that thin layer we have to fabricate our device. For example, we have made it n plus, here we have made it n plus. Okay, then we have had a particular p-type region. Okay, then again here we have p plus land, again here we have p plus land, and then here we have the n plus region. Okay, how they have been fabricated, that each and every step we are not discussing, but what we are doing is what we can see is, now this particular NMOS transistor, okay, this particular NMOS transistor and this PMOS transistors are electrically isolated. Why it is isolated? Because in between we are having the insulator. Okay, in between we are having one insulator. Fine. So because of this insulator, right, because of this insulator, these two devices are not interacting to each other. So when they are not interacting to each other, it is not having any parasitic component. So because of that, the device operation is not going to be affected. Okay, it is not going to be affected. So we have to understand that in the silicon on insulator, that whatever we want to discuss, the whole sole purpose of this discussion is that we have to make a such structure. Okay, we have to make such a structure in which all the components should be electrically isolated. If they are not isolated, okay, if they are not isolated, it will be having a particular parasitic components, and that parasitic component is going to affect the device operation. So basically what we need to have is, so if it is a cross-sectional view, if you see from the top, okay, just I have drawn it, okay, to make you understand, if there are billion number of transistors, let us say, and if we see it from the top, okay, all these devices should be isolated. Okay, if there are, let us say, device D1, D2, D3, D4, D5, D6, there are so many devices. Okay, then all these devices should be isolated, should be electrically isolated. Okay, there should be no parasitic component that should be found in between. Okay, from here itself we can see it should be isolated. Again, if we see from the top side, it should be isolated from all other components. Okay, whether it is placed anywhere, okay, either it is left, top, bottom, okay, or the right side, wherever. So wherever it may be, it should be electrically isolated from their adjacent or their neighboring devices. Okay, so that isolation we have to provide. Fine. So now, because we need to have the isolation, okay, of the device so that we can avoid the our parasitic elements. So there are basically three techniques that are available for the isolation. One of the call is the locus, okay, which is known as the local oxidation. Its full form is the local oxidation technique. Okay, and the second one is the shallow trench isolation, or otherwise we can also use the silicone insulator device. These are all the isolation techniques. Okay, so basically in the local oxidation, again, if you go back to the previous picture, and you could have seen that at the gate, wherever we need a particular silicon device like NMOS transistor or PMOS transistor, there we had a very thin layer of oxide. Okay, at the gate terminal, okay, between the gate and the channel. So we had a very thin oxide. Okay, but wherever we do not want any device at that time, we need to have a very thick oxide layer. Okay, we have to have a very thick oxide layer. So that can be done by the local oxidation. Okay, so generally this local oxidation is not preferred because there is a Bird's beak problem. Okay, there is one problem which is called as the Bird's beak. Okay, and that's why this particular low cost technique is not followed very much. Fine, but we can use the low cost technique as you can understand, like a very preliminary, it is very preliminary stage, or you can say a very simple technique that provide you the isolation, but because of the Bird's beak problem it cannot be used. Okay, now in the shallow trench isolation, I will be explaining this one just for the sake of completeness. Okay, and then we will be discussing on the silicon insulator. So basically in the shallow trench isolation, what we do is, first of all, we are taking a substrate. Okay, so this substrate was initially up to this point. Okay, you just try to understand this one. So it was initially it was up to this point. Okay, so first we have to take the substrate like this, and then within this substrate, what we have to do is we have to form a different wells. Okay, like first we have to grow the N well at this point, then we have grown the P well, again we have grown the N well. Okay, so that way we can grow the different wells wherever we need. Okay, so that can be done by a simple diffusion technique. So after doing these wells, after growing these wells, what we are doing is we are having a pad oxide over here, and then over this we are having a silicon nitride. Okay, so this will be used as a masks. Okay, and after having this one, okay, so it will be completely covered, you can imagine it. Okay, so initially it must be covered like this. Okay, it was covered like this. So here we are having a complete substrate initially up to this complete substrate structure, and within this substrate we have performed the doping, and by doping we have grown the wells, like N well here we have grown the P well here, over here, then we have grown the N well here. Okay, and this is covered with the pad oxide, and one is called as silicon nitride. Okay, which is acting like a mask. Okay, so we have grown these two layers. Now after growing these two layers, what we have to do is we have to etch out these portions. Okay, we have to etch out these portions to make it electrically isolated. These wells should be made electrically isolated. Okay, because we have to fabricate our device within these wells only. Okay, within these wells only we have to fabricate the device. Okay, and these two layers will be acting like a mask. So what we have to do is we have to etch out this particular substrate region. Okay, this region was not initially doped, so it was undoped region. So this silicon substrate has to be removed first. Okay, this has to be removed first. So we have to etch out this particular region. So we can call it as a trench etching. Okay, we are removing this particular region and it is acting like a trench. So we can say it is a trench removing or trench etching. Okay, so we can remove this trench. So after removing this trench, what we have to do is we have to grow a very thin oxide. Okay, a linear oxidation we have to perform so that the exposed silicon should be covered with the oxygen. Okay, SiO2 layer. So then it is covered with the SiO2 layer, and again we have to perform the chemical vapor deposition, and completely it should be isolated by again depositing the SiO2 layer. So basically these two layers are your SiO2 layer only. Okay, it is not a different layers. So once we achieve this, but this type of layer, okay, this type of layer, now what you can see is we have to uh, make it planar. Okay, because in the planar process this top surface should be plane. Okay, so what we have to do is we have to do the planarization. So in this planarization what we have to do is we have to remove this particular layers. Okay, this particular pad oxide we have to remove, or we have to remove the silicon nitride layer. So this should be removed through a particular chemical etching processing. Okay, so once we remove it, okay, once we remove it, after removing this one, we are going to get this type of a structure. Okay, finally we are going to get this, but this particular type of structure. So this is done by having a CMP. Okay, CMP stands for your chemical mechanical planarization process, polishing. Okay, chemical mechanical polishing, right? So this particular processing we have to follow. Fine. So after following this process, this type of a structure we will be getting. So now within this structure, you can see that we are having a substrate over here. Fine. P types of substrate we are having in this region. And then this is our N well. So within the N well, we can fabricate our PMOS transistor. Okay. Then again, we are having a P well over here. And this N well and P well is actually electrically isolated by having this SiO2 layer. Okay, again this P well and this N well is again having a isolation. So again it is having a trench oxide, you can say, or it is SiO2 layer. So now within this wells, this N well, this P well, okay, within these wells we can fabricate our devices. So basically what is the basic difference that we can see from the our bulk CMOS structure? In the bulk CMOS structure, our devices was actually made within the conductive substrate. Okay, but here within the conductive substrate we are not making any device. Okay, we are not making any device within the substrate, but rather we are making the devices into this well structures, like in this N well, this P well, and this N well. And these N wells and P wells are electrically isolated. Okay, so when it is electrically isolated, there will be no parasitic elements between them, and because of that there will be no such detrimental effect while operating it. Fine. So this way we can perform a isolation. So similarly, the way we have done the isolation by using the shallow trench isolation, similarly we can also do the isolation by following the silicon on insulator. This type of structure we can fabricate, and with by fabricating this type of a structure, it can also provide you the isolation. Okay, we can make isolated lands onto which we can fabricate our devices. So there are basically two types of silicon on insulator structure we can see. One is like you can see here this SOI types silicon on insulator. So one is we can have a substrate, and onto this substrate we have to have a particular buried silicon oxide layer. Okay, we have to form a particular buried silicon oxide layer, and after having this buried silicon oxide layer, okay, we have to grow a small or thin layer of silicon, and within that silicon layer we have to fabricate our NMOS or PMOS transistors. Okay, as you have seen in the previous case. Okay, so this is a little bit different from what we have seen in the trench isolation. Okay, so in the trench isolation we had the substrate and directly we had this particular layer. Okay, but in the silicon on insulator what we are having is this silicon layer is actually deposited over a particular insulator. Fine. So buried silicon dioxide, basically it is a silicon oxide we are talking about, silicon dioxide. Okay. So when we are having a silicon dioxide layer over here, fine, then this is your insulator. Okay, it is having the insulating property, and because of the silicon dioxide, it is having insulating property. Onto this particular insulator we are fabricating a silicon layer first, and within that silicon layer we are fabricating our devices. So that's why we are calling it as a silicon on insulator. Okay, so this, because it is a silicon on insulator, so there is no such foundation that it should be always a silicon oxide. Okay, it is not a foundation like it is always a silicon oxide. Okay, it can be our silicon nitride also. Okay, it can be any insulator which can be a suitable, which will be suitable for fabricating a devices. So it can be silicon nitride also, Si3 and 4. Okay, or it can also be a sapphire. Okay, sapphire is our Al2O3. Okay, so that is our sapphire. So either we can take the sapphire directly, which is again a insulator. Directly we can take the sapphire, and onto this sapphire we can grow a silicon layer, and within that silicon layer we can fabricate our devices. Okay, so when it is silicon on sapphire, it is also called as SOS. Okay, silicon on sapphire. Or if it is silicon on insulator, if it is silicon dioxide, or if it is silicon nitride, then it is called as SOI. Okay, but both are your silicon on insulator structure only. Okay, both are your silicon on insulator structure. So this way we have to fabricate our device. So what is the motive? Obviously the motive is to this. Okay, we have to isolate the devices. Whatever the device we are going to fabricate, these devices should be electrically isolated. Okay, so in this way it is having a silicon substrate, and onto the silicon. So basically in the SOI structure, what we do, we are having a silicon substrate, then we have to form a oxide layer. Okay, oxide, buried oxide layer. Okay, whose thickness is about 0.1 to 1 micrometer, and then we have to grow a thin layer of the silicon, and within the thin layer of the silicon we have to fabricate our devices. Okay, so this is our SOI, basic structure of our SOI. Fine. So now what we have to do is, in fabricating this particular SOI, as we have already seen that, okay, so basically in silicon on insulator devices, as we already seen that what is the necessity of this device is to reduce the parasitic components. Okay, basically parasitic capacitances. Okay, we have to make the devices electrically isolated. Okay, so that what we are doing is, we are onto the substrate, we are fabricating one oxide layer, and onto that particular oxide layer we are fabricating a thin silicon layer, into which we have to make the devices. Fine. So basically what we are saying is, the devices are built in a thin silicon film on insulator. Okay, maybe SiO2 or Si3N4 or sapphire. Okay, insulator can be formed by performing high energy implant of suitable atoms. Okay, so basically this particular buried oxide layer is actually implanted by having uh, this oxygen ions. Okay, so basically a very high energetic oxygen ions should be bombarded onto this particular structure. Okay, so that is done. So either it is oxygen molecule, oxygen atoms or ions can be sent, or it can be a nitrogen atom that can be sent. Okay, so based on what kind of atoms, what particular elements we are choosing for forming the our insulator, it is either called as CMOS, or it may be called as the SIMNI. Okay, so where the CMOS stands for separation by implantation of oxygen. Okay, separation by implantation of oxygen, and it is actually first reported by Izumi. Okay, it is called as CMOS. So you just try to understand what is the CMOS means. CMOS means separation by implantation of oxygen. Similarly, what is SIMNI? It is separation by implantation of nitrogen. Okay, so we have to implant the nitrogen there. Okay, so basically if we perform this one, then obviously it is going to reduce the parasitic capacitances, and once the capacitance is reduced, obviously it will increase the device speed. Okay, this is one of the biggest advantages. Okay, it is also reducing the power consumption of the devices. Okay, it is also consuming the less power. Devices are consuming less power. Okay, some complexity actually increasing, but obviously it is advantageous for our device operations. Fine. So let us suppose that if we want to follow the CMOS process, okay, we want to grow the SiO layer, okay, SiO2 layer, okay. So while growing the silicon on insulator, okay, if we want to implant the oxygen, okay, generally if we want to implant the oxygen, then it is actually done by these two processes. What is called the CMOS, basically three processes, okay. It is CMOS or it is BSOI. BSOI stands for the bonded and HVAC technology, or we can also follow like a dielectric isolation, okay. So these are the different ways by which we can make this particular SOI structure. Okay. So basically this CMOS is one of the method which is very much popularly used. And this third one is also used, dielectric isolation. This technique is not that much popular. Fine. So basically in the CMOS, okay, in the CMOS what we are doing is, first of all we have to take the silicon substrate. Okay, normally we have taken it from the Czochralski crystal growth, whatever we have studied so far, or float zone method. So we have to take the wafers, okay, of a particular doping, P type substrate or N type substrate as per our requirement, and then we have to implant the ions of oxygens. Okay, a very heavy dose of oxygen will be implanted. Okay. So when implant the very heavy dose of oxygen, so that should be of the order of 10 to the power 18 per centimeter square. Okay, this much of heavy dose we have to implant. Okay, that will be done with very high energy, right? So the high energy implantation of oxygen, actually it is done at this much of energy, 150 to 300 kilo electron volts. Fine. So this much of energy will be used for implanting this oxygen ions into this particular layer. So once we do it, as we know that, because by bombarding or implantation, this particular surface will become amorphous. Okay, it will leave this particular surface amorphous and it will damage it, okay, because of the bombardment. So to just reduce or minimize the damaging of this particular surface, we have to keep this substrate at least at 400 degrees centigrade. Okay, we have to keep this temperature at least about 400 degrees centigrade. And once this operation is done, this implantation is done, we have to go for the high temperature annealing process. Okay, so what we have to do is we have to increase the temperature a lot. Okay, and it should be go up to 1300 degrees centigrade or 1400 degrees centigrade, and that should be kept at for several hours. Okay, and then it will be forming a particular SiO2 layer. Fine, and this way it will be forming a buried layer of SiO2. Fine. So this way finally we can get the layer, and then again we can go for the silicon deposition. Okay, we can go for the silicon deposition. And within the silicon, again we can fabricate the devices and we can make the isolations. Like we have seen in the trench isolation, we can do the isolation and then we can fabricate the devices. Fine. So this is our SOI structure. Okay, using the CMOS process. Okay. Uh, Another structure like by following the dielectric isolation. Okay, you can again follow the dielectric isolation. So how this can be performed, dielectric isolation? First of all, we have to take the substrate, and within the substrate we have to cut the grooves, okay, of this type of shape. You have to cut the groups, not only two, just for the explanation purpose we have taken the two groups like this. And then within this group what we have to do is we have to, over this group we have to deposit the polysilicon. Before that we have to uh, grow the oxide layer. Before growing the polysilicon we have to grow the oxide layer, a very thin oxide layer we have to grow. So first we have to grow the thin oxide layer and then we have to grow the polysilicon. So this type of a structure will be formed first. Okay. So after getting this type of a structure, just we have to turn over this particular wafer. Okay, we have to turn over this particular wafer and then we have to grind it. okay, when you grind it from the bottom side and just turn it over, okay, then obviously we are going to get this type of structure. You just see we have just turn it over, so this structure will come to the bottom. This is showing downward, so it will come upward. Okay, it is showing upward here, it is showing upward here, and now this structure has to be grind. Okay, so once we grind it, okay, we remove the top layer from here, okay, in this fashion. Okay, we remove it like this. Okay, after removing we will be getting this type of structure. Okay, so now within this structure, okay, within this structure, now you can see that we are getting one of the substrate. Okay, we are getting one of the substrate which is electrically isolated from this part and this part. Okay, so this substrate is not, now this island is actually getting isolated because of this groove cuttings. Okay, so now this is isolated. Again we can have another groove at this point. Okay, so if we have another groove at this point, another isolated region we can found, another isolated region we can found at this point also, similarly at this point also. So now within this substrate we can fabricate our devices. Okay, and these devices are now electrically isolated. Okay, because of this oxide layer, we are having an oxide layer over this point. Okay, so this will be your electrically isolated islands within which we can fabricate our devices. So this way we can fabricate our uh, devices onto a silicon, like in by following the SOI structure, silicon on insulator structure. So try to understand, this is basically an isolation technique. SOI is basically an isolation technique. So within this, by using this particular isolation technique, we can have the advantage that we can reduce the parasitic elements, capacitances, elements like capacitances or transistors, and thereby we can improve the performance of the device. So I hope you must have learned something from this discussion. So thank you for watching this lecture. We will be continuing in the next lecture. Thank you.